Let us talk about data access from disk. Access from disk is a very important area to know because, as you understand, that we are talking about advanced database. So we must have an understanding of data storage in the disk and how actually we can efficiently design query or the query engine in order to retrieve data very nicely. So take a look at the next immediate discussion is we need to talk about disk here, data access from disk, software-based optimizations, prefetching block, and choosing the right block size. So take a look at a typical disk. If you see on one hand, you have head assembly, and these are actually read-write heads of with an arm, and these are actually the disk platters. So what happens? The read-write arm move forward and come back in the head assembly, and on the other hand you see, take a look at a disk platter. It has a very nicely logically curved tracks. These are actually concentric circle. These are tracks, and you have specific sector within the track, and there are gaps also. The gaps are actually inter-sector distance, and we generally have these are actually areas which is automatically block when you are actually formatting a disk. The difference between unformatted disk and formatted disk, the size wise, unformatted disk is higher than the formatted disk. After formatting, what happens, this track and the sector addressing occupies certain amount of storage. That's why you see formatted capacity is always lower than unformatted capacity. And what are the terms we have? We say platter, head, cylinder, track, sector. Sector is a physical and block is logical, and there is a gap between that. So talking about block address, we have physical device, number of cylinders, surface, and start sector. And the most important thing we have to have, just to again take you back to the previous, it is characterized by all these physical issues of cylinder, surface, and start sector and the physical device. So disk access time is a very important concept because the disk prices are varying based on its access time, because the lower the access time, the fast is the access, and it is much expensive. So the latency is very important. So latency generally answers this question. I want X block, and the block X is in the memory. How much time it takes for transferring the block X into the memory, which is the latency. That means latency is a time which is taken by the system to locate the data and to retrieve the data and transfer the data. So that's the kind of thing happens. So what is this access time? As you see, seek time plus rotational delay plus transfer time and others. So that means you are trying to understand the access time. Access time depends on how much time it takes to seek, and there is a rotation. Why? Because the data is actually located at different sectors and on different platter. So you need to have a rotation to get that data location and the next data location, and then you have a transfer time and plus others. So generally it happens to be like this. A seek time, if you see the cylinder versus time chart, is always like, it's like a little bit of exponential happens to be. Average time is between 10 millisecond to 40 millisecond. So the cylinder traveled is almost like at a certain number of cylinder, you have almost a fixed time, So the seek time increases as you are moving towards the cylinder. Yeah. So rotational delay, you can understand the head is here and the block one you want is here. So there is a rotation. In fact, in order to get this block under the head, in order to do read write. So there is a rotation, and this is a rotational delay. So what happens, average rotational delay is generally half revolution. I generally say that it's 8.33 millisecond if it is 3600 RPM, revolution per minute. But the present disk are more than even 15,000 or 20,000 RPM. It's very fast. All right. So transfer rate T is generally about 1 to 100 MB per second. You see, so it's a block size over time. So the block size over time is actually the transfer time. How much time it takes to transfer a block. So other delays that we have is the CPU time, central processing unit time, to issue input output. Contention for controller, why? Because contention is common. Sometimes there is a conflict and it's automatically resolved that conflict in the hardware. And contention in the bus and memory also, because you're trying to go somewhere and find that cannot, so change the path and go again. That's a kind of contention issue. So contention is a very important issue in hardware. And typical value generally we expect to be 0. We don't consider that. So for random disk access and reading next block comes in like this. If we do things right, times to get the next block size over t plus some amount of negligible timing, skip gap, switch track once in a while and next cylinder and so on. But overall, this is actually how we get the seek time. But what is the rule of thumb? The rule of thumb is, if it is random input output is expansive, sequential input output much less. 1 kilobyte of block random IO generally about 20 millisecond. But if it is a sequential, it's actually almost 1 millisecond. So it's 1/20th. It's so fast. So cost of writing similar to reading, unless we want to verify. So read write, there should not be any difference in terms of cost. Cost is in terms of time. So to modify a block, we need to read the block, modify in memory, write back. So this is happening to be always like this. So you read, you modify in the memory, and then write back. So this read and write operation is continuous on the disk. So a synthetic example, you can see it's 3.5, 3.5 in dia, 3.5-inch diameter disk, 3600 RPM. There is only one surface, 16 MB usable capacity, and it's about 128 cylinder. What you mean by cylinder is like, if you look at the concentric ring of you remember the disk surface with concentric ring, and if you take out each ring is a cylinder. So that's how actually you look at cylinder. 128 cylinder means we have 128 concentric rings on the disk surface, and the seek time average is 25 millisecond, and adjacent cylinders are 5 millisecond. So 1 kilobyte of block size is actually sectors. That means sector is 1 KB, 10% overload. It's a typical example. So 3600 RPM, 60 revolutions per second. One revolution is at this millisecond. These are the other tracks. So time over useful data. These are typical calculation and example you can see here. But burst bandwidth is about 1 KB is 0.117 millisecond. And you have a burst bandwidth, we mean that how much data is transferred from the memory to the disk, or the disk to the memory. So sustained bandwidth over track, you can see it's over track is 128 KB in 16.66 millisecond. So it's actually, you're dividing now by the time, you get about 7.68 kilobyte per millisecond. So that's kind of chunk we can actually read or we can write. So time to read one random block is seek time plus rotational delay plus transfer time. So seek time means you're going and locating the location of the data. There is a rotational delay and then the transferring of data time. So this is about you're adding this 3 time to get this total read time. And a block to envelope calculation is also like this. Suppose it takes 25 milliseconds to read 1 kilobyte block, and there are 10 tuples of size 100 byte each to fit in one block. How much time? So you basically do the calculation. Suppose DBMS deals with 4 kilobyte blocks, 1 to 4 kilobyte. This is actually one block. And you basically have T4, that means you're talking about the time, you can understand. This time is 25 millisecond, then you divide 16.66 by 2, and then this is actually your transfer time, one block. So it's all together about 33.83 millisecond, but you can understand the difference between T1 compared to T1 is 33.45 millisecond and the T4. So it's actually taking a little bit more time. We can go back to understand a little bit here. This is a rotational delay, you can understand, and that was the transfer time. But in case of, it is a random block, but when we talk about 4 blocks, and you can see here, it's actually random blocks, but the difference, you won't find much difference here. It's a fraction of time differences, because you added actually another timing for beside this transfer time, it's the read block time. So you remember again that how much time to read one table containing 1 million records is an example from this point of view. And here I can go back and take you to further. So time to read a full track, this is to get to the first block, you see, and then the time, the rest of the time is about this. So actually a bit less. We do not have to read the last gap, you understand this. So this is actually what we talked about: mix access and software-based optimization, prefetching block, and choose the right blocks. So software-based optimization in Dix controller, we actually have prefetching blocks and other things, and I appreciate that you understand this part. We have prefetching blocks exploit locality of access, because prefetching blocks helps improve faster efficiencies, improve performance by hiding access latency, and need extra buffer space, because double buffering, why? Because the data should be available beforehand. So the block size selection is a big block. Amortize input output cost, because you don't have to go further again and again in the disk and come out like that. So unfortunately, big block read in more useless stuff, because you are reading lots of data which you may not use. Yeah. So trade-off: small relation, update heavier workload, difficult to use block larger than the track, multiple block size. So with this, we stop here, and I'm sure you continue learning database. Thank you so much.